Good afternoon, everyone. Thanks for joining. I'm going to talk a little bit about kind of some trends and some threads for how to develop architectures as we go forward in the world of the cloud. As an industry, are transitioning away from traditional compute models, the old server-centric, client-server-centric ones, enterprise-centric, with private and dedicated assets were moved over to the cloud. I wanted to share some of the thoughts that we have in terms of how to architect and build for this new world. Let's see if I can figure out. Okay, we'll just use the old mechanical way. So over the last decade or so, we have all witnessed the emergence of the cloud and the rapid growth. And you can see from this that the cloud is ascendant. As you look at, it is fair to say that at this point now, the cloud is starting to be the dominant compute paradigm. It is starting to eclipse, as you can see, what came before. It's not really completely eradicated it, but it's starting to eclipse it. In fact, in 2018, it is projected that the volumes for cloud servers will actually overshadow those for traditional compute. And the revenue will also be about 50%. So I think it's fair to say that the compute paradigms are changed. We are now at the cusp of a new era, and maybe already halfway into it, as you can tell from the volumes. So, and the new compute paradigm that is emerging is the cloud one, and we probably have the opportunity to use that as the basis for what we build for the future. Now, as we look at what's actually going on inside the cloud, what is actually running, you'll see that there's a emergence of whole new classes of workloads, whole new classes of algorithms, and the software building blocks that are used are completely different as well. Many of these were not really in existence or even a few years ago, and even today they're rapidly evolving. So as this is happening, what we see is that we have new workloads, new software building blocks, new algorithms. So not only is the compute paradigm changed, the underlying building blocks are also substantially revamped. And what that gives us is an opportunity to essentially look at architecting for this new world. Now, what we have is these usages and workloads, they're driving a different set of requirements than what we had before. You have a completely different set of types of computation that need to happen. You have the demands on memory and I/O are evolving in many different ways and different from what they historically were. And there's a need to deploy at speed and scale. So as we think about architecting for these future products and for the cloud, there are a few threads that I think are worth paying attention to. If I were to summarize that in kind of one sentence, it is to be able to efficiently and securely deliver the best performance across a broad range of workloads and freeing ourselves from the unnecessary backwards-looking constraints that we've been subject to before. And giving, in addition to that, giving our customers the freedom and flexibility to evolve their cloud infrastructure as their needs evolve. Now, it's clearly feasible to deploy these systems with legacy paradigms and with legacy systems. In fact, that's really what we're doing today. But in my mind, this cloud represents a new optimization point. And it is now dominant, and it is growing. And we should build for it, not just reuse or repurpose what was built before. And I think that is kind of the key point that I want to make going forward. So as I talked about efficiency, and we all know that in the cloud arena, the total cost of ownership, TCO, is the primary criterion for decisions about cloud deployments. So architecting for the cloud implies paying attention to the key drivers of TCO, which are CapEx, capital expenditure, what you pay for buy, and OpEx, which is what you spend as you run the data centers. And central to this concept of optimizing TCO, both CapEx and OpEx, is really is efficiency, and that's about minimizing waste. What this means in practice is that the systems we are actually deploying out there are the systems we're deploying out there are actually utilized at the full extent that we deploy them. So in other words, sorry, my screen has gone. Apologize for a second. Could I get a bit of help here? Okay, we'll keep going. What this means in practice, as I mentioned, is that the systems we are, so we want to be able to essentially deploy systems and be actually fully able to use them. What we find is that we do not want a system where we've built out a capacity and are leaving capacity stranded. And so in that context, what we want to do is we want to utilize both in a physical sense the space as well as the power that is actually allocated to these data centers. We want to use all of it. So a big piece of that is actually what we're finding is we want to integrate more and more functionality in. And smart integration is necessary both for density, because density, usable density, where we're actually using all of the area where we've allocated and all the infrastructure we've allocated, is pretty important. And so as a result of that, what we want to do is integrate as much of the functionality into our components, into the heart of the system, the processor, as much as possible. And this includes, in particular, things like I/O, as well as other system components that are actually quite standardized and are necessary for just getting the systems going. We don't want there to be essentially a lot of waste in the system because of that. And this actually saves both not just area by consolidating everything into the central processing units, but also it consolidates, it reduces power, and it saves cost by reducing unnecessary BOM items. So integration is a pretty important piece. Okay. Is it disappeared? It's over there, okay. Well, come on back. All right. So the other part, I think, in terms of efficiency is power. Integration brings power savings and improved power efficiency. In looking at hyperscale data centers and speaking to folks who build them, what you find is one of the more visible sort of eyesores is the fact that you have all this capacity and there are racks that are sitting there partially populated. And the reason for that is because the systems that are being deployed are too power hungry. So power efficiency is really a critical element of what we believe is and needs to be the important, a critical vector for architecting new generations of products. Now, while rack power budgets vary across different regions, what I think is constant is that when a data center is deployed with a particular power envelope, that all of that power needs to be used, as I mentioned earlier. So in that context, I think it's important to integrate and reduce power with that. It's important, in addition, to actually deploy all the technologies we have at our disposal for this. So for example, we really want to be able to be on the leading edge, the most leading edge process, silicon processes. We want to be able to get the lowest power for all of our key elements. We want to apply the most advanced power states and to develop and deploy algorithms for power management and power savings that are not just static and built in hardware, but are actually able to evolve over time as we learn about how the systems are deployed, and are able to actually learn autonomously about what the right power savings algorithms are. So power efficiency, I think, is a fairly important piece going forward in our architecture for the future. And if we do that, then we will be able to utilize all of the space and the resources that we have deployed for our data center. Now I'm going to switch from the efficiency aspect, which I think is pretty critical in the cloud space, to performance, which is ultimately we're all about delivering, getting a bunch of work done. And so power efficiency and space efficiency and integration are important, but at the end of the day, you have to do some work, which is running the workloads and the algorithms. As we look into the cloud workloads, what we find is that they are quite demanding in terms of memory. They require both a very high degree of capacity. Increasingly, these workloads are operating on, analyzing very large sets of data. And they want to be able to keep that data as close to the compute as possible, and they want it to be able to access it very quickly, so very low latency, and at a very high, with very high bandwidth. So you have the three things that you have to balance across: capacity, bandwidth, and latency. And as we look forward, increasingly, we're incorporating persistence into our memory hierarchy as well. So those are pretty important things as we look forward. The architectures that we are building need to be optimized for these aspects of the memory. The memory subsystem is perhaps one of the more important pieces now of our, most important pieces of our systems. So memory is important. The next important piece is compute. You actually have to do all the operations. And what we find is that there's been lots of experimentation in terms of compute performance, and lots of different design points exist out in the industry. But what we think is that what we really need is balanced compute. So Amdahl's law is still in effect. So there's still some parts of all workloads, even the very highly parallel ones, that require good ST, single-threaded performance. So that is a pretty important piece. But in addition, we need lots of threads, not just a few threads, not just a limited number of threads, but lots of threads, because the software stack has now figured out how to use lots of stacks, lots of threads. Between the parallelization efforts and the scale-out efforts, we have the ability to utilize lots of threads. And what we want is real threads, not kind of junior threads. We want to be able to use full compute capability of a CPU, not have it be distributed across multiple threads. So that's it on the compute side. Now, I think there's a lot of workloads that really do quite well with the existing set of general-purpose CPUs. But there's a set of emerging workloads that actually require different kinds of compute, different kinds of interconnections between the compute elements. And for those, I think there's a variety of things we need to do in order to accelerate them. The more straightforward thing what we'll want to do is we have the ability as the algorithms mature, as we understand the characteristics better, we need to actually take that and put that into the general purpose CPUs as instructions. So you have to evolve the instruction set architecture to optimize, to improve the performance of these workloads. So that's not easy, but it's straightforward. But the additional thing is there's a lot of these algorithms that are still evolving, that are developing very quickly, and they're not well suited to being integrated into the CPU cores. And in those cases, I think we have to be able to do a number of different things. One, be able to have excellent capability, both from a bandwidth and latency and I/O connectivity standpoint, to connect these accelerators that are custom accelerators. Maybe they're ASICs, maybe there's GPUs, maybe there's FPGAs, be able to connect them. And then, in addition, we want to be able to have, in some cases, we will actually want to take some of those accelerators and integrate them onto the die. Maybe they don't fit really quite well into the CPU itself, but they belong on the silicon because of the close cooperation that they have. Now, so as I mentioned, flexible acceleration for new and emerging algorithms. The next piece I mentioned earlier about was security. So security, I think we've all been, we've seen all of the publicity around, various exploits, various, Spectre and Meltdown are the ones that are most common in on our memory right now because they just came up recently. But the reality is that in addition to those sort of exploits, there is a need essentially for us in the cloud to actually provide a higher guarantee of security and trust than perhaps even in historical contexts with historical computing paradigms where the assets are all owned by a particular entity. So in a cloud world, you have this thing called multi-tenancy, as you know, and multi-tenancy means that there are multiple folks who are from different entities, maybe even competing entities, maybe adversaries, who might be sharing the same infrastructure. And as they're sharing the infrastructure, they might be sharing it temporarily, at the same time they're using it, maybe in a virtualized environment, or maybe one person uses it and then because it's a cloud and it gets repurposed and redeployed to somebody else, you might have that situation where it's over time you have different people on the same machine. And what's very important is the ability to ensure and to provide assurances from an architectural level that those assets that each of those entities had are not able to be stripped or hacked or taken over by somebody else. So that, security and trusted security is a pretty important piece based on fundamental building blocks in the hardware. That's one of the important things we need to do in security. Now, I'm going to talk a little bit now about the freedom aspect of it. And I think there's two ways that freedom as a thread kind of goes through what we want to do looking forward in developing for the cloud. One is that the systems themselves, there's a rapidly evolving landscape we talked about, both in terms of workloads and in terms of algorithms. And what we want to be able to do is able to extend the systems that folks have deployed out there. The ability to extend that is going to be critical, and it needs to be done based on open standards, open industry standards, open community standards, not just things that have open in the word, but are actually truly open. So as you extend, you want to have different accelerators attaching. They should be able to attach on industry standard interfaces. They should be able to communicate with each other using industry standard interfaces. When you want to create large systems and have fabrics connecting them, they should be based on industry standards because in our belief, the things are moving fast, rapidly evolving. In order for for us to keep pace, we need to be able to use the speed of the large open community. Having walled gardens is not the best way to get speed in evolution. Finally, what I would say on the architecture front is that we are coming from a previous computing paradigm. The cloud, as I mentioned, represents a new optimization point. And I think one of the things that we have as an industry to look at is how do we wean ourselves from the legacy burdens and not burden the cloud architectures and the cloud products we develop with those legacy burdens. And I think that's in terms of the legacy that we have in terms of prior software stacks, expectations of compatibility with those stacks, expectations of what the metrics of performance are, and expectations of even what is reliability in a cloud environment versus reliability in the historical paradigm. Those are different. How you deal with that is different. So in my opinion, we have the opportunity here to build an architecture and a set of products that are designed for what comes next, not for the historical backward-looking view. So essentially, as we look to build what comes next in computing, I would suggest that we need to look for an architecture that supports this new rapidly evolving landscape. And I think it should be built on those 4 pillars. That's certainly how we're approaching it. And if we do our jobs right, and I'm confident we will actually be able to develop products that are built for this new optimization point, and we can unleash the real power of cloud computing. Now, as you might know, I work for Ampere Computing, and we are in the process of executing to that vision that we just talked about. We have multiple generations of products in development, but as we have a booth as well, and we'd invite you and welcome you to come and visit us in booth A32. And with that, thank you. I have a minute or two for questions. Hi.
Do you talk about the workloads or categorizing them as arrival rates and burst sizes, anything like that when you categorize the workloads?
So the question is, do we categorize workloads? Absolutely, we do. We both look at classes of workloads, and then for particular workloads, we do categorize their both compute and I/O and memory kind of characteristics in order to understand how to optimize for them.
So what would be the range of arrival rates, burst sizes, and gaps that you would expect?
So the question is, what's the range of arrival rates? I think there's a number of different vectors and parameters, and that's probably a conversation for the booth, maybe. Any other questions? Okay, if not, I'll let you go 1 minute early. Thank you so much.